Well, my dear participants, now I am going to talk about odds ratio analysis. Let us study topping performance of imported and local sires in the sheep breeding farm, Sher-e Kashmir University of Agricultural Sciences of Kashmir, Srinagar. The main aim of the data is to compare the topping performance of local and imported sires in terms of their topping performance. Let us create a data matrix topping of frequencies first. Topping is equal to matrix C 30, 25, this is a real data, 20 and 45, n call is equal to 2. Then dime names, it is local versus imported, and then topping performance, not topped, topped. So it gives the output like this. Topping performance, not topped and topped. Sires local and imported. It was imported was Australian Merino. So now whether imported have a better performance as compared to local, this is the question. So define a new function that is known as odds ratio analysis. Actually, this odds ratio we have defined like this. Say for example, this is the data. The data matrix is like this. Here 30 and then 20 and then 25 and then 45. So odds ratio analysis is nothing but odds ratio is 30 into 45 divided by this. So odds ratio is equal to 30 into 45 divided by 20 into 25. So this is known as odds ratio. Odds ratio measure, it was introduced by Evarts in epidemiological situations, but it can be used anywhere. Odds ratio has certain advantages over test of proportions that we shall talk later. So if we want to test this, we have to use logarithmic transformation. So log of odds ratio estimate divided by standard error of divided by SE of odds log of odds ratio, log of odds ratio. So, and this follows normal 0, 1. This follows normal 0, 1. So, this SE is nothing but SE is equal to square root of 1 by n11, n11 is this one, n12 is this one, n121 is this one, n22 is this one. So it is n11 plus 1 by n11 n12 plus 1 by n121 and plus 1 by n22. So these are the inverses of these values. So that is nothing but standard error. It has been obtained by using delta method. So it is a different concept. It has been approximated by, this is an approximate test. So to compute, and it's, see here we have defined a function which computes odds ratio and then it estimates standard error. It is 1 by x11, see, and then z is equal to log of odds ratio divided by SC, and SC is nothing but this. So p value is twice into 1 minus p norm absolute value of z, and least odds ratio is equal to OR z value z, p value p value. So dump this function and file is odds ratio .txt source. So here odds ratio gets 2.7, See, first I would like to define odds ratio function of x. This is a data matrix. X is equal to s dot matrix to ensure that the object is a matrix, and then odds ratio is equal to x11, the first element, first diagonal element, then second diagonal element divided by x12 non-diagonal element into x21, and standard error is the inverses of these elements, and z is equal to log of OR, logs of odds ratio divided by SC, and p value is twice into 1 minus p norm absolute value of z. List odds ratio is equal to OR, the estimate of OR, z value, see this is z value is z, the value of z is statistic, and p value is equal to p value which is being here. Then we are dumping this, and the file is odds ratio.txt. Then source odds ratio tupping is the data, this tupping is the data object. So as soon as we give tupping, it gives the results odds ratio of tupping performance. Odds ratio is 2.7 and z value is 2.60 and p value is 0.0092. So p value 0.0092, it is much less than 0.05. That means we are rejecting our hypothesis. And see, in chi-square test also we make this kind of inference. If we will use chi-sq dot test tupping, we will make the same inference. But here the association between tupping and Sayre is quantified here. It is 2.7. Interpret the results as there is 2.7 times more likelihood of tupping for imported as compared to local. So here we are interpreting this result. See, there is 2.7 times more likelihood for imported of tupping as compared to local. So this is the interpretation of this result. So we are quantifying that odds ratio, and this statement is statistically significant also. It is evident from the p value, which is p value 0.009, which is less than 0.05. One can get the corresponding result of the chi-square test, chi-sq dot test. So here p value is 0.01. Again the same result we are getting, but there is no interpretation of this type which is always there with odds ratio analysis. So this odds ratio analysis is always better than chi-square test of independence. Now graphic features, mosaic plot we can have. See, tupping, mosaic plot of tupping. See, imported, not tupped, it is lesser area, whereas imported and tupped, it is more. So that means imported are having more likelihood of tupping as compared to non-tupped, whereas locals, not tupped, it is more, and tupping, local, it is less. So this mosaic plot describes this table. So this is the graphical interpretation of tupping performance. Mosaic plot of tupping data shows the graphic view of the data present in the contingency table. Tupping performance of imported Sayres is better than the locals. It is 2.7 times more for locals, for imported Sayre as compared to local. Now if we go into the source file, we can run these commands: xtabs, sugar, data is patient. So this is f out, See, this is sugar versus age. Sugar is the first dimension and age is this one. Then prop.table F out 1. 1 stands for row wise proportion. So it gives row wise proportion and it is 15% and 84%, 85%, then 85% and 14%. Then odds ratio analysis I have already talked. Then if we run this, see how we are creating this matrix. We have entered the data column wise 30, 25, 20, 45. So we have created the object topping. So this is the data. Now we are naming rows and columns. So for that the function is dime names topping, list, sires. This is the first dimension name, that is rows, sire. Sire is equal to local imported. And then topping performance, this is the second argument, topping performance C, not topped. So when we give dime names and if we print this, it gives dime names. Sire, local versus imported, topping performance, not topped. So this way this data has been created. Now we are going to define the odds ratio function, odds ratio, the function of x is the matrix. So x is equal to as dot matrix. Odds ratio is equal to x11, the diagonal element, into another diagonal element, x11 into x22, divided by the non-diagonal elements, multiplied by non-diagonal elements. Then S standard error is equal to square root of, it is because of delta method. You can have the standard results in any text on categorical data analysis, like Alan Agresti's categorical data analysis. So SQRT 1 by x11 plus 1 by x12 plus 1 by x21. So these are the inverses of these elements. These are the inverses of these elements. So log odds, z is equal to log of odds ratio divided by standard error of this, and this is z value. So when we run this, so we are getting, and then we can dump odds ratio file is equal to dump, and then we can make use of the source and the file name is odds ratio .txt. So we have to give the file name odds ratio because it is a text file. Odds ratio, oh, the file name is wrongly written. Source odds ratio.txt, odds ratio.txt, file is dumped. Actually, odds ratio.txt, odds ratio.txt, SOO, the file, the name of the function is wrong, source. So it has been sourced. Sourced means the function which has been defined, we can call that, it is equivalent to running this whole function. It is equivalent to running this whole function. So one can send you the code as a text file and you can make use of source to source it. Then execute these commands, see source, and then odds ratio is the function and X matrix is topping. This is equivalent to odds ratio is the function and x object x is equal to topping. So it is topping. So the value of odds ratio is 2.7, z value is 2.60, p value 0.0092, and odds ratio x is equal to same results. So this 2.7 is interpreted like this. Say topping. So this 2.7 is interpreted like this. There is 2.7 times more likelihood of topping for imported as compared to local. So this is the interpretation. There is 2.7 times more likelihood for imported of topping as compared to local. So this is the interpretation of this result. And this p value shows that it is significant. So we have already interpreted. Same results we can get by using chi-square dot test, but here interpretation of this kind is not available. It is just we are concluding that there is significant association between topping and type of sire and nothing more, but here we are quantifying 2.7 times more likelihood for imported as compared to local. So this kind of interpretation is only available with odds ratio analysis. Now graphic comparison. See here, topping, see topped, local is less, and not topped, local is more, whereas not topped, imported is less, and topped, it has more area. So this shows that imported have more likelihood of topping as compared to local. So this is the mosaic plots interpretation. Now I am going to talk about analysis of variance. So far we have completed our categorical data analysis. Now I am going to talk about another technique of analysis, and that is known as analysis of variance. Analysis of variance is a technique in which we partition the total variation in the data due to assignable and unassignable causes of variation. We shall discuss data available with package far away. It is due to Julian Faraway 2022. This is the data discussed in Julian Faraway. The coagulation data set comes from the study of blood coagulation times. 24 animals were randomly assigned to 4 different diets and sample were taken in a random order. Details of the data has been as actually this data set, coagulation data set, has been discussed by a great scientist, that is George Box. So they have discussed this data set in Box, Hunter and Hunter. They are the authors, and the title of the book is Statistics for Experimenters. And the same data has been discussed in the Gilman's book also in a different scenario. Gilman's book is Bayesian data analysis. So see, what is the analysis of variance? Analysis of variance technique was introduced by Sir Ronald Fisher when he joined Rothamsted Station in 1919, and he continued on design of experiments, and he developed many terms like variance, analysis of variance, sufficient statistics, consistency. So all these terms were developed by Sir Ronald Fisher, and the analysis of variance was also introduced and term was developed by the Sir Ronald Fisher, the father of statistics. Require far away, we have to install far away package and then require our library far away. Then head coagulation. It is coagulation time of the 4 type of diet. So this is the type of diet A, B, tail, coag diet, coag and diet. So these are the type D. C, data frame, 24 observations of 2 variables, coag numeric, coagulation time and diet factor with 4 levels A, B, C, D. Table coagulation diet. See this table coagulation diet, we are making this frequency table of diet. So how many observations are there in A group? There are 4 observations. In second group, B group, the 6 animals have been given this type B food and 6 animals have been given type C food, and D group is given 8 D food is given to the 8 animals. So this way table coagulation diet we can get the results. From the above table, it is evident that there were 4 animals assigned to diet A, whereas 6 animals to diet B and C and 8 animals to diet D. Now we shall explore the data as below. Get summary of results. Summary coagulation. So coagulation is a numeric data. So here minimum is 56, coagulation time is 56 and maximum is 71. The first quartile is 61.75, median is 63.50 and mean is 64.0 and third quartile is 67.0. And diet is the factor variable, it is a categorical variable. So it is given just frequencies. A has 4 frequency, B is 6, C has 6 and D has 8. Get means for each diet. Get means for each diet. See, the function t apply we are using. So the first argument of t apply is the numeric vector, and here this is the categorical vector and this is the summary features which we want. So t apply, we apply on coagulation, the coagulation diet. Diet is the categorical variable and mean is the function. So it is A mean is 61, B mean is 66, C is 68 and D is again 61. So these are the means. T apply, get standard deviation of coagulation time for each diet. T apply coagulation coag, this is the numeric variable, coag diet, this is the categorical variable and this is the SD. So SD we want. See the SD of B is maximum followed by D and then A and then C. T apply standard error of mean. For each group we want to define standard error of mean. So what we have done, T apply coagulation, coag, coagulation diet, this is the categorical variable, this is the categorical variable and function, here we are not writing any standard function, we are going to define a function and that is a function of x, SD divided by square root of length of x. So this is nothing but standard error of mean. See, standard error of mean is defined like this. See, SC of mean is defined as SD divided by square root of n. So this is known as standard error of mean, S by square root of. So this expression has been implemented here, SD of x divided by square root of length of x. So for each group we are computing standard error of mean. Now we are plotting coag diet data is equal to coagulation. So here this is numeric, this is numeric and this is categorical, this is a factor variable diet. So if we are having numeric here and numeric here, then it gives a scatter plot. But if we are having numeric on y-axis and on x-axis we are having a factor variable diet, then it will give you a box plot. So it is giving box plot. Box plot, coag, diet, data is equal to coagulation. So this is the box plot of the data. See here, this is the median of the median coagulation time of A. This one is the median coagulation time of B. This one is the median coagulation time of C. And this one is the median coagulation time of D. See, the median coagulation time of A and D, they are close, whereas they are different. So they are differing. Highest coagulation time is in the treatment C, followed by B, followed by D, and then A. So these are the plot. This is known as, this is the lower whisker and this is the upper whisker. And here this talks about the symmetry of the data also. From this box plot, it is evident that means of diet A and D are similar. Means are similar because these are the means or medians. Medians similar. And lower than the means of diet B and C. Diet B and C. Moreover, there is less variability in diet C as compared to A, B, C, D. So there is less variability in diet C because length of the box shows the variability present in the data. So in the diet C, length of the box is least, so it has least variability as compared to these. Now, how can we fit one-way ANOVA model? For this data, for the data of this kind, coag, and this is the data for this kind is, the model for this kind is, the model can be defined as Yij, this is the response coagulation time, is equal to mu. Mu is the overall mean, plus alpha I is the effect of ith diet, and Eij is the random error part. So where Yij is the response coagulation time of ith diet and jth animal, mu is the overall mean effect, alpha I is the effect of ith diet, and Eij is the random error. Note that Eij is normal with mean 0 and variance sigma square. Now this model has been fitted using LM. LM stands for linear model coagulation. Coag, this is the coagulation time, coag versus diet. This is the effect of diet. So this one and this one, they are not part of the model. They are understood to have. So coag versus diet, data is equal to coagulation, and summary of results. See here, these are the residual standard errors, and see coefficients, diet B, diet C and diet D. But diet A is absent. Actually, this is known as treatment contrast. In the treatment contrast, we compare, we have a reference like if you say to someone that, oh, you are very smart, but the question is that smart with whom, with compared to whom. Suppose someone says that you are smarter than Amir Khan, then certainly Amir Khan has become the reference. Similarly, in genetic trials, in horticultural experiments, suppose you are generating you are creating a new variety, you are developing a new variety. So you have claimed that this variety is best. So there is always a reference that as compared to which variety it is best. So here the diet B, diet C, diet D, but diet A is not there. Diet A is not there. So this has become the reference group. So it is actually diet B versus diet A, because the difference of, if you look into the difference, see the means 61. So 66 minus 61 is 5. Similarly, diet C 68 minus this is 2, and here it is 0. So this reference has come here. See, diet, this is diet B versus diet A. A has come into the intercept. This is 61. So diet B versus diet A. This is the difference. Diet C versus diet A. This is the difference. Diet D versus diet A. So this is the difference. This is, and then standard error, and then T value, and C the P value. So diet B versus diet A, it is significant. Diet C versus diet A, it is again significant. But diet D versus diet A, both are having 61, 61. So here it is not significant. It is not significant. So this is the interpretation. From above output, it is evident that row intercept represents mean of the diet A, whereas rows diet represents the contrast of mean B versus mean of A. Similarly, diet C represents contrast of mean C versus mean of A, and diet D represents the contrast of D versus A, D versus A. Moreover, it is evident that diet B and diet C are significant, whereas diet D is not. Now, if we will use the function AOV to fit this model, what kind of output we will get, and that I will discuss in my next lecture.